Okay, welcome to today's session. Let's wait for a few minutes and then we'll start. Today we'll firstly introduce the band twisting and how topological and trivial insulators are different in terms of band twisting, let's say, and then we will solve some problems, or I'll just give some hints about the assignment 3. Okay, again most of the problems are solved in the lectures itself, but yeah. Okay, so it seems nobody is joining now. So let's start. So initially, so in the first part we will study trivial insulator, and then we will move to the topological insulator case. Sorry. So for the trivial insulator, we will take a model which is something like there are two kinds of atoms in a unit cell. So this is the unit cell, okay, and so there are A kind of atom and B kind of atom, and there is intra unit cell hopping, which is minus T. So intra unit cell hopping is equivalent to or characterized by minus T, okay, and there is no inter uh, unit cell hopping. So there is no hopping, this kind of hopping, okay, and this is periodic. There are n such unit cells, so total number of unit cell is equal to n. Now these are just model, okay, so you can ask question that if the unit cell between the unit cell there are no interaction at all, there is no hopping or yeah, there is no hopping at all, then how the solid state system forms, right? Because there must be some kind of interaction between the unit cells or among the unit cell itself also, that binds them together. So these are some extreme limits, okay, where we are ignoring the inter unit cell hopping parameter, this kind of inter unit cell hopping parameter. So you can think of that there are some hopping actually, which is, let's say, T prime, which is inter unit cell, okay, and T is much greater than T prime. So for analytical tractability and more intuition that we can get from the this kind of model, we just make that you can just think of that intra unit cell hopping parameter T is much larger than inter unit cell hopping, okay. While this doesn't represent any actual scenario where this is the extreme limit where T is some finite not equal to 0 and T prime is absolutely 0, but in this limit we can find models, realistic models where this limit is valid, okay. So we just want to understand the physics, and we for that we construct different models so that we can understand the physics simply as possible. And then of course we have a numerical ways of doing things where we can take everything into account, okay, of course within our numerical ability, I mean computation limitation limit, okay. So you have a unit cell like this, and there is a system with total number of unit cell is n. So there are two orbitals in the unit cell, one is corresponding to A and one is corresponding to B, right? Two orbital in the unit cell. So if there is two orbital in the unit cell and each of the hopping parameters is just minus T, then what will be its eigen energy values? So it will simply be eigen energy will simply be plus minus T. Now just to see how this happens, so you can simply construct a Hamiltonian which will be, let's say, this represents A kind of atom and this represents B kind of atom, and I am saying that there is no on-site potential. So so an electron sitting at A site doesn't feel any energy as long as it doesn't go to B, let's say. So this is A, this is B. So self energy of the electrons at site A is 0, and when it hops from A to B it is minus T, and the vice versa, right? Hermitian conjugate, when it hops from B to A it is also minus T, so minus T, and this is again 0. So there is no self energy or there is no self energy or on site potential at the B site also. So if this is the Hamiltonian, then you can simply think or simply calculate that minus epsilon, minus epsilon, and then minus t minus epsilon mod equal to 0, right? So this will simply be epsilon square and minus t square equal to 0. This implies that epsilon square equal to t square, epsilon equal to plus minus t. This is the simple solution, right? So and this is also expected if you have two orbital, if you can think or just remember the I think class 12 chemistry or even physics, basic physics course, there will be formation of anti-bonding and bonding orbitals, right? So anti-bonding orbitals are higher in energy, not preferable, and bonding orbitals are lower in energy, so more preferable, let's say. So epsilon equal to t is higher in energy, and we can call it anti-bonding orbitals, and this looks something like if I draw E site and B site, something like this one, okay. And on the other hand, epsilon equal to minus t, lower in energy, which is ground state in our case, it is bonding orbital. And in this case, it will be simply, let's see, A, B, okay. So this kind of, so the orbitals are centered at A site and B site, and if you find the eigenvectors corresponding to these eigenvalues, so let's say, so u plus I am denoting, this is for the positive energy, for epsilon equal to plus t, you will find that it 1 by root 2 minus 1 by root 2 simply, okay. And similarly u minus, which is u minus, which is for epsilon equal to minus t, ground state or bonding orbitals, it will simply be 1 by root 2 and 1 by root 2, and you can just check this actually. So you take h plus u, you will get that epsilon, I mean you will get plus t, and then you will get back u plus, or similarly, okay, plus minus t, okay. So this is just a easy check. So so these are the single particle wave functions. So this was for the one single cell, and so you have a one unit cell. So what is happening is that one unit cell give rise to two energy state, right? And that is because there are two orbitals corresponding to two orbitals present in a unit cell corresponding to two sites. You can generalize this that two sites A and B. You can generalize this that A site have multiple orbitals, which is realistically definitely possible, but for simplicity we are just considering just one orbital per atom, okay. Okay, so these are the so what will be the single particle spectrum or single particle spectrum? It will simply be, so this is the energy, and somewhere this is plus t and somewhere this is minus t. Let's say this is the zero energy, okay. And how many energy states are there? So in one unit cell you have two energy states. So let me write this. In one unit cell, 2 energy state. So this implies that we have n unit cell. Since we have n unit cell in the system, meaning there will be 2n energy state in the overall system. Okay. So this will so so this minus t will be consist of n states. N such state will be in the minus t, and then there in the plus t state there will be another n states. Okay, together it makes two n states. Things will be clear why we are doing this and what is the relation of this with the uh, atomic normal trivial insulator and topological insulator. Now so this was the sort of clear from the real space picture itself that we have a unit cell or system such that a unit cell consists of two orbitals, a type and b type. Each site has only one orbital, and there is a intra unit cell hopping parameter minus t, and there is no inter unit cell hopping parameter. Okay, so we have total 2n number of such states. One will be at lower energy minus t, which is ground state, and another will be at plus t, which will be excited states. Let's say plus t or excited states or higher energy states corresponds to antibonding orbitals, and the lower energy states corresponds to bonding orbitals. Okay, so far so good. This was sort of mostly real space view. Now let's look at what happens to the momentum space picture of the same thing. So in the momentum space, or so if you start with the momentum space, okay, so since nobody was there, I started the trivial and topological insulator as I promised last time. So I am repeating. Okay, so okay, by the way, before going to the trivial and topological insulator, so do you have any questions or any queries from the assignments that we can solve in the later part? Initially, let's understand the trivial and topological insulator. Okay, so in the momentum space, or in the real space or Hamiltonian, if we write in terms of second quantization notation, so minus t sum over I is the indexing of the unit cell. I denotes the first unit cell, second unit cell, and so on. So we have CIA dagger CIB plus Hermitian conjugate of that, right? So note that there is no inter unit cell hopping. So I denotes the unit cell. Unit cell index. Okay, so if you see, there is no inter unit cell. Whenever there is a inter unit cell hopping, you will see, you will observe that there will be terms involving I and I plus 1, right? If we consider only the next nearest neighbor hopping, only next nearest neighbor hopping. So this kind of term, so kind of, let's say CIB dagger CI plus 1A. So this kind of term you will get when there will be inter unit cell hopping. Inter unit cell hopping, but we are not considering that, we will consider that later. So this is the real space Hamiltonian. So now if you just Fourier transform that, so ft Fourier transform, you will get k space Hamiltonian or the momentum space Hamiltonian. Simply looks like sum over k minus t ckA dagger ckB plus Hermitian conjugate. Okay. So this is the momentum space Hamiltonian. So again, so initially we had 2n number of states. Here also again we will have 2n number of states, or per unit cell there will be only 2 states. That is also evident from the structure of the Hamiltonian itself, and as well as because of the fact that Fourier transform do not change the energy eigenvalues, right. So you are just going from one space to another, this does not change the energy eigenvalues. So again 2n energy states, for each value of k. Okay. Now similar to the previous case, we can again form again there will be bonding orbital, anti-bonding orbital. So you can write bonding orbital corresponding to energy equal to minus t. So the wave function can simply be written as ckA dagger plus ckB dagger. So creation operator corresponding to A site and B site 1 by root 2 and omega, and this omega is the ground state or vacuum state, actually vacuum state. Okay. So once you operate the creation operator on the vacuum state, you create states, and so this is the bonding state or bonding orbital, and then there is, similar to the previous case, anti-bonding orbital or anti-bonding states corresponding to energy equal to plus t excited state, which will be u plus equal to ckA dagger minus ckB dagger by root 2 omega. Okay. So basically again same thing, the energy eigenvalues. So this is the energy, and so let us say, so this is energy equal to 0, rather 0, and these are the k values. So you start from k equal to minus pi to, let us say, k equal to plus pi, right. Okay. This is plus t and this is minus t. So minus t plus t, and the gap between this is obviously 2t. Okay. So the same thing basically in the momentum space also. Now to proceed further, let us consider half filling case. So what do we mean by half filling? So there are total 2n states, right. So there are total 2n states, and half filling meaning half of the states will be filled. So sorry. So since we have 2n number of states, so 2n states, that means that half filling means n states will be filled. So let me write completely. Half filling in our case implies, so half into 2n equal to n states are filled, right? So n states are filled, so obviously the states will be filled from the lowest energy, right? Ground state will be filled first, so these are filled states. So remember that these consist of n state and another n states are at the higher energy, so these states are all filled. Okay, ground state is fully filled. So in real space you can view this half filling case as B, A, B and so on. There are total n number of unit cell. So here one electron is there, another electron is there, and so on. So this is the real space picture. Okay, half filling. And in the momentum space, this is the picture. So you have bands, two bands, and the lower band is completely filled. That is the half filling. And so if I, so here, so let me draw again here to contrast. Okay, so this is the real space picture. And this is the momentum space. And so the wave function, many body wave function is simply sum over I, or the products of I goes from 1 to the number of unit cell n, CIA dagger plus CIB dagger by root 2. So we are taking only the bonding state, because in the half filled case only the bonding states will be fully filled, right? And in the momentum case again same thing, product of all the k states, all combination of k, ck dagger plus ckb dagger root 2 and operating on the vacuum state. Okay, so this actually shows, so if you look at this picture, so the electrons are sitting at the unit cell. So this is the unit cell, right? This is one unit cell, and the electrons are, I mean, frozen at that unit cell. So electrons are not allowed to hop from one unit cell to another unit cell. So this is what we call actually atomic insulator also in the real space. So this is nothing but the atomic insulator. Okay, why atomic insulator? Because as if the electrons are centered or frozen around some atoms. In this case it is frozen around within the unit cell itself. The electrons cannot hop, so they cannot move, and as a result when you apply electric field or external perturbation, they do not conduct electricity. Okay, that's why we call it insulator. And this is also evident from the energy spectrum. So this is the energy spectrum in the k space. You see that one energy state is lying here at minus t and another energy state at plus t, and there is a energy gap of this amount 2t. So so this is definitely an insulator, right? Okay, so so in real space picture we can call it atomic insulator, and in momentum space this is more familiar with the name of band insulator. So bands are basically isolated, there is a finite gap, so that when we apply external perturbation, they are sort of they do not conduct electricity. So So this amount of energy, 2T amount of energy needs from one from for electrons to go from the minus T energy state to plus T energy states. Okay. Okay, so this is an example of saying a band insulator can be thought of as an atomic insulator actually. Okay. Now in the so far we assume that this hopping from within a unit cell itself, of course, from A to B atoms was just constant, and that was given by minus T, right. Now what happens if the hoppings are uh, not constant minus T, but some function of energy, momentum, let us say. So now we are in a momentum space picture. No, so let us say now imagine a Hamiltonian something like H equal to sum over K epsilon of K, or let us say epsilon 0 of K CKA dagger CKB dagger no dagger plus CKB dagger CKA, simply Hermitian conjugate, right. And we assume that epsilon 0 of K is greater than 0 for all K, all values of K. Okay. So now contrast this Hamiltonian with the momentum space Hamiltonian we had this case. Okay. So the only change that I have made is that minus T goes to epsilon of K, right. So this is the only thing that I made, no change at all apart from this. So and since the epsilon 0 K is some function of K, it is not a constant unlike previous case. The energy eigenvalues will be exactly same and the wave function will also be same, right. So again there will be two states, bonding and antibonding. Bonding will be given by CKA dagger plus CKB dagger by root 2 product of all K operating on vacuum state, and then again there is antibonding state product of K CKA dagger minus CKB dagger by root 2 operating on vacuum state. This is because epsilon K changes nothing actually. It's a not it's a parameter which is varying at each K, but then for each K you can have the same thing because epsilon K doesn't change sign itself, right. So then our band picture can look like something like this. So this is now a function of K. So maybe something like this. Okay. So maybe this can be one of the bands, let us say, depending on how epsilon 0 K is there. So this is minus pi, this is let us say K axis, and this is where somewhere here this is plus pi. Okay. So the ground state is still given by this bonding state, right. Nothing changed apart from epsilon 0 is a function of K. So now the question is, we have seen atomic insulator where atoms are electrons are frozen within the unit cell or around some atoms, let us say, and even if you have some some Hamiltonian something like this where the energy or the hopping energy depends on different K, which in case of real space or in terms of real space it depends on the which site I am in, let us say. Even then the bonding states or antibonding states or the states remain same as long as epsilon K is greater than 0, things are insulated, right. So again there is a gap, although the gap is not same at every K, but there is a gap. So essentially this is still an insulator. So still an band insulator. right. So essentially what we have is that there are a bunch of insulator which are identical as kind of atomic insulators, which doesn't conduct electricity and so on upon providing external perturbation. Now the question that we ask in order to understand or distinguish between the topological insulator and trivial insulator example is this one that we are discussing. Uh, Later it will be clear why we are calling trivial and non-trivial, that is topological. So there are a bunch of insulators which we can model you can think of, which are just there is a gap in the energy spectrum, and if we think of like uh, half filled case, again in this case also half filled case, the electrons will be only occupied in this particular ground state, and this will be free, completely free, the higher energy will be completely free. So again this will be insulating, right, in the half filled case. Remember that when we call it insulator, so when you ask the question that what is an insulator, or if we give an, or if we provide an I mean band structure and then call it is it an insulator or not, the question itself doesn't have any meaning. So if we be more specific, so let's say we have a band something like this, okay, and so the question is it an insulator? Is it an insulator? Okay. uh, as long as you do not call or you do not say that Fermi, where the Fermi energy lies, you cannot tell that it is an insulator. So if we have a Fermi energy somewhere here, that means electron from here cannot go to this another band, so it will behave as kind of insulator. But if we have a Fermi energy somewhere here, then these are, let's say, these are field states, okay, and when you give electric field or any kind of external perturbation sensitive to electronic motion, then suppose we have electron here, and then or let's say here you give external perturbation, and then it can immediately go back to the, or it can immediately jump to the excited state or higher energy state. So once the electrons are able to change their state from one energy state to another state, essentially there is a conduction, or the motion of electron is happening, right. So this conducts electricity and so on, so this doesn't become an insulator. So it is an important to say that to ask the question, whenever we ask the question of insulator, whether a material is insulator or not, the question will be, immediate question will be, where is the Fermi energy lies. Similarly here also the same case, if there is, here is Fermi energy, then insulator, so electrons here can jump from this state to this state, and then electron, I mean electricity conducts, so it's not an insulator. So this is the reason why we stick to the half filling case. Okay, so in our model we took half filling case, because in the half filling case the lowest energy state, that is this state, will be completely filled, and there is because there is a energy gap, so the electrons cannot go from this state to this state. So essentially it's behave as a uh, I mean insulator. Now if we have not considered that half filling case, let's say somewhere more than half filling case, so for the half filling case the lowest energy states will be completely filled, and then the extra amount of filling goes into occupying this higher energy state. So let's say somewhere here you have a filling such that the Fermi energy lies here, or uh, this states, these states, okay, highlighting in pink, these states are occupied within the band. So then again you are encountering this kind of case, this case or this case, so it is not an insulator. Since we are our aim is to distinguish or understand how trivial insulator is different from the topological insulator or non-trivial insulator, so we will stick to the half filling case, so that we are in the insulating regime, and then we will see what is the difference between topological and non topological or trivial. Okay, so this was a little bit of I mean distraction, kind of necessary distraction, let's say. Now let's consider another case to understand how these I mean things are different. I mean all insulator are not same basically. Okay. Okay. So consider another system or Hamiltonian, let's say. So again we will take two sides A and B. So this is the unit cell, okay, one unit cell, and this time we choose the model such that there is a hopping between these two states. Okay, simply minus t minus t and so on. Okay, in the both side. So now we have inter unit cell hopping. Which is again minus t, constant case. Okay, and this is the first unit cell, and these two makes, I mean let me draw fully. So this is the second unit cell, this is first unit cell, and then third and so on. Okay, fourth, third, fourth, and so on. So again you can if you think real space from a real space perspective, nothing has actually changed. You have just changed the Hamilton, I mean hopping parameter from the intra cell to intra unit cell to inter unit cell. So again there are only two orbitals within the unit cell. One is corresponding to A, on another one is corresponding to B, and then now there is no uh, hopping between A and B within the unit cell, rather it is the with the next unit cell, right, from B to A or A to B. So if you think from a real space perspective or any perspective actually, again we will have two energy states, simply plus T, let me use different colors. So energies are basically again plus T and minus T, because Hamiltonian still remains similar. Okay, so you have uh, energy plus T and minus T. Again you will have anti-bonding states and bonding states, and the bonding states or bonding orbitals will have, bonding orbitals can be written as, or states can be written as, in the real space I is sum over all the unit cell. So CIB dagger plus CI plus 1, this is important, by root 2 and acting on the vacuum state. Okay, so the only change that I made is that now there is a Ci plus 1. because these are the I mean, so this is the ith unit cell, let us say, and so if we consider this is ith unit cell and this is I plus 1, right. So ith unit cells B atom is interacting with the I plus 1th unit cells A atom, right. So CIB dagger corresponding to this atom, and then Ci plus 1A corresponding to this atom. Okay. Rest of the things remains same. Now now again it is an atomic insulator, of course, because energy states are T and minus T, again we will have some energy, I mean the bands are at different energy. So if you consider half filling, it is an insulator. So let me write again. Half filling. Now the important difference is that it is a bit different, okay, and the difference you can only already see from this picture, in the hopping picture, as well as from this part. So in the ground state or the bonding orbitals, now you have Ci plus 1A instead of Cia, okay. So energy is same as the previous case, but things are different now. So let's look at why this is different and how it is different. So again we will go back to the momentum space case or the picture. So so you have a Hamiltonian, real space Hamiltonian looks like something like this, minus T, then we have CIB dagger, Ci plus 1 A plus Ci plus 1 A dagger CIB, right. So this is the real space Hamiltonian. Now again we will do the Fourier transform. Fourier transform can be done as CIA or B, whatever it is. Dagger goes to 1 by root over L. L is the units, I mean total length of the system, let us say. Sum over K e to the power I K dot R. R is the position. You can just write also X, C K A dagger. Okay. So again usual Fourier transform. Now if you do this, and yeah, so if you do this, the momentum space Hamiltonian will look like sum over K, again minus T, similar to the previous case, C K B dagger, C K K A, and another extra e to the power minus I K plus C K A dagger, C K B e to the power plus I K. Now I will explain why this extra I K comes. This I K actually comes because of this factor e to the power I K dot R, okay. So initially in the previous case we didn't have any R. R means it has to be I mean out of unit cell distance. I mean if once you go from one unit cell to another unit cell, then only it counts, in our case, in this case at least, okay. So this distance is, let us say, unit. So from this to this is, let us say, unit in our case, okay. So r equal to 1 we assumed, unit distance, I mean unit cells are apart from each other at a unit distance, or more precisely this distance from B to A, this is unity, okay. So in the previous case we had a Hamiltonian like C I A dagger C I B, right, and in the Fourier transform we didn't have any R because we are within the unit cell itself, two atoms are there within the unit cell. Now in this case we are going from one unit cell to another, and this distance is, let us say, unit, okay. So then e to the power I k dot r, r is unit. So, you will pick up an extra e to the power I k, and for the Hermitian conjugate you will get an e to the power minus I k, or the vice versa. Okay. So, this is the source of e to the power I k, and it turns out this will be playing an important role. So, okay, so let me highlight, these are the two important, I mean one important thing that will distinguish from the previous case. And yeah, so if you write the Hamiltonian, so in the so this Hamiltonian is essentially equivalent to sum over k minus t c k a dagger c k b dagger, and then 2 by 2 0. We do not have any one side potential, electron does not feel any energy when they are at the B site itself, but when there is a hopping from B to A or A to B, there is an energy cost, which is minus t into e to the power I k and e to the power minus I k, let us say, and 0, and this is the. So, this is just the basic tide bending Hamilton, I mean tide bending tide bending information or knowledge I am using. Okay. So, this is the form of Hamiltonian. So, h k is simply minus t 0 e to the power I k e to the power minus I k 0. Okay. So, so if you just evaluate the energy eigenvalues just by I mean evaluating the determinant, you will simply again see. So, let me evaluate actually. So, h k, I mean, so energy eigenvalues can be determined as minus epsilon minus t e to the power I k, sorry, yeah, nothing, and minus t to the power minus I k minus epsilon equal to 0, right. So, epsilon square minus t square e to the power I k into e to the power minus I k equal to 0. So, this implies again it will be plus minus t. So, energies are essentially same, but you already see the difference in the Hamiltonian itself, as well as so when we talked about real space case, the orbitals are already different because of this term, right, C I plus 1 dagger. And Hamiltonian, of course, these are the two terms, I mean phase, there is a phase factor e to the power minus I k which is distinguished. So, energies are same. Now, if you so you use these energies to determine what will be the antibonding and bonding orbitals in the momentum space. So, eigenstates, let us say, eigenstates in momentum space, you will find that so corresponding to energy equal to minus t, you will find that u minus will be equivalent to 1 by root 2 1 e to the power minus I k, and for energy equal to plus t, u plus will be 1 by root 2 1 minus e to the power minus I k. Okay. So, you see the similarity. Okay. So, I can put minus 1 here just to distinguish it more. So, you see the similarity, you just have the similar almost same thing, it is just that you picked up an e to the power I k and minus k. Okay. And in the momentum space again you will have ground state, in the momentum space will be something like k c k a dagger plus e to the power minus I k c k b dagger 1 by root 2 and omega. Omega is the vacuum state. So the only important point or difference is that there is an interesting phase sitting here in the wave function itself, right? So phase factor. The moment you turn on the inter unit cell hopping, or the when the inter unit cell hopping is stronger than the intra unit cell hopping, there is an interesting phase that comes out, and this phase will determine the characterize the topologically non trivial state, as we will see later. Okay, so we'll take a small aside, necessary aside, to emphasize on the importance or the the importance of this phase and how this phase determines the topology. So, let's consider, and so this is this. So before that, let's remind ourselves that this is a two component wave function, right? Two component wave vector or wave function, and this two component wave function can always be represented in general in the polar coordinates. So, for higher component wave function, what do? We need higher dimensional coordinate system. Okay. So, let us say we have x, y and z axis, and so we have a vector somewhere here, and this is the theta of the polar coordinates, and this is the phi, right? So, remember in the previous class or the previous to previous class, we said that any Hamiltonian can be any 2 by 2 Hamiltonian can be written in general in terms of d of k dot sigma, right? And this d k dot sigma can also be written, I mean the sigmas are the Pauli matrices. So, the general form of this Hamiltonian uh, in the polar coordinate system, you can write as cos theta sin theta e to the power minus I phi sin theta e to the power plus I phi minus cos theta, right. So, this you can any 2 by 2 Hamiltonian you can parameterize as this one, okay, and theta will have some function, theta will be some function of dk, dx, dy, dz and so on, so is phi. And one simple example I think you can remember this is that I mean spin in magnetic field in the quantum mechanics, basic quantum mechanics books of Griffiths, let us say. Okay. So, any 2 by 2 Hamiltonian you can map like this one. Okay. In fact, this is similar to considering a magnetic field, I mean a spin in a magnetic field in a 3D magnetic field, let us say. In general, it has x, y and z all components. And for this Hamiltonian, eigenvalues are plus minus 1 simply, okay, and the eigenstates are given by cos theta by 2, sin theta by 2 e to the power I phi and another states will be given by so I think this will be for the positive energy states. Yeah, so this will be for the positive energy states +1, and for negative energy states it will be cos theta by 2, no, it will be sin theta by, it will be reverse, minus cos theta by 2 e to the power I phi minus I phi, no, it is already minus, so e to the power simply I phi. Okay, so this is for the energy -1, and these are for this Hamiltonian. Now you can easily generalize this for our Hamiltonian case already, because uh, our Hamiltonian is also, so this is our Hamiltonian, so this is also 2 by 2, and you can just equivalently write things down, right? In our energy is plus minus t, here it is plus minus 1, so you can easily parameterize these things. So what is important is that so now uh, let's look at, so this is the ground state Hamiltonian, right? Sorry, ground state wave function for this Hamiltonian, ground state wave function, right? Now in our case, so take the example of case 1, where we had intra cell hopping, intra unit cell, case 1 hopping. So we had a wave function like or the ground state wave function was something like products of all k combination ckA dagger plus ckB dagger by √2 acting on the vacuum states, or simply the u minus single particle wave function. So this is the many particle and this is the single particle case, simply it was 1 1 and 1 over √2, right? So this was the anti-bonding states or the ground states, let's say. Now we compare this wave function with this one, ground state of this Hamiltonian. So this Hamiltonian represents or the so this is the Hamiltonian we are considering and comparing, because the eigenstates are represented or can be represented by a vector in this 3D coordinate system. Okay, uh, again characterized by theta and phi and so on. So you compare this wave function, our previous case 1 inter unit cell hopping ground state, with this one. Okay, so what will you find? Sin theta by 2 is 1 or 1 by √2, let's say. So comparing, so let me give some number, some a and some b. Okay, comparing a and b, so what will you find? Sin theta by 2 is simply 1 by √2. What that does mean? We have theta by 2 equal to pi by 4. So this means theta equal to pi by 2, right? And minus cos theta by 2 e to the power I phi. So minus cos theta by 2 e to the power I phi equal to 1 by √2, right? So we already know theta by 2, I mean theta equal to pi by 2. So cos theta by 2 means cos pi by 4, again 1 by √2. So minus 1 by √2 e to the power I phi equal to 1 by √2. So this will give me so e to the power I phi equal to -1. That means phi equal to pi and or the multiple of odd pi, let's say, right? 2n plus 1 pi. But within, in our case, in our convention, phi is pi, because phi can take 0 to 2 pi, so phi is pi. Okay, so this was the case 1. So if we draw this, I mean this wave function b corresponding to b in the polar coordinates, so what does it look like? So x, y, z, and So I'll denote so this wave function, depending on the theta and phi, it will have a vector notation, right? In a general case it is theta and phi, we have a vector notation like this. In our case we got phi equal to, so let me sort this also. So we got theta equal to pi by 2, theta equal to pi by 2 meaning all the vectors will lie in the xy plane, right, because this is pi by 2 in the xy plane, and then phi equal to pi. So sorry, okay, so you can start from 0 actually. I think I missed something. Just a minute. Yeah, it's okay actually. So phi equal to pi. So so phi equal to pi means, if you see from this expression, I mean this coordinate system, so phi equal to pi means it will go and direct along minus x axis, right? So the vectors are along this direction, with the vectors corresponding to this equation B, which is the trivial case, case 1 ground state, looks like something like this. So in the Brillouin zone it starts from let us say minus pi, right, k goes from minus pi to k goes to plus pi. So k and k, and somewhere in the middle there is k equal to 0 point. So it actually in the xy plane, and it is opposite to x, so minus x, and all are actually parallel. So although in the from the drawing it doesn't look like, but all are parallel. So all vectors are, what does that mean is that at each k the wave function directs along the same direction. So at each k point the wave function along directs along, is directed along minus x direction, right? So this was the case for the type 1, or I mean the case 1 where intra unit cell hopping was there. Now let's come to the case 2. Okay, so inter unit cell later case, hopping is equivalent to minus t. Okay, okay, so in this case many particle wave function was simply sum over k, or products over k, ck a dagger plus e to the power minus ik ckb 1 by root 2 acting on vacuum state, or we had u minus equal to 1 e to the power minus ik, or it was plus. Let me see. e to the power minus I k and root 2, no, yeah, and 1 by root 2, right. So this was the case. Now again, if you so let's call it C, and if you compare equation A and C, what will you find is that again theta equal to pi by 2 like previous case. Now the important difference is that so we have so 1 by root 2 to the power minus I k equal to equation A was minus cos theta by 2 e to the power I phi. So minus cos theta by 2 is simply in our case 1 by root 2 e to the power I phi, right. So e to the power I phi equal to minus e to the power minus I k. So these are the two conditions we get. In the previous case we got phi equal to pi. So all the vectors or the wave vectors at each k point was directed in the opposite direction of x, right, minus x axis. In this case the contrast is that although the wave vectors lie in the xy plane, so this determines that wave vectors xy plane, but because of this k dependence of the phi determined by this equation, we have the vectors are not along the same direction unlike the previous case. So if you draw this, so something like this will be, so start from minus pi to pi, and this should be symmetric, okay, but something like, so maybe minus pi and then starts in opposite direction, completely opposite direction, again it changes its direction. So this is the vector field. So this is essentially nothing but mapping a state at each k point, mapping a state at each k point with the vector field, or in terms of yeah, in terms of vector field, right. So why this change happens? Because we know that phi can change from 0 to 2 pi, and within that span of 0 to 2 pi you can change sign, okay, unlike the previous case where it was constant. Okay, so this is a clear contrast with the previous case. Now if I so since in the momentum space Brillouin zone, or in the Brillouin zone picture, minus pi and pi are the same point basically, so you can draw these vector fields in the I mean you can close this loop. So okay, so this was the type 1, let's say. I will explain what is means, sorry, or case 1 rather. Case 2, okay. So in the previous case, so assume that this is the positive x direction. So in the case 1 we had, let's say, so all vectors are along the minus x direction, right. So, this was the case 1. Now, for case 2, if we, so you need to visualize a bit. So, so you have a line something like this one, it goes from minus pi to pi, and so it always kind of a twisted, right. Now, if we I mean take these 2 points end points and kind of touch each other, then what will happen, uh, so you can think this as a I mean yeah, you can think this as a comb. You have a comb, and you are just making it round shaped circle type, right. Then what will happen is that your vector fields or those strains will look like something like this. So, all are outward. Okay. Okay. So, this is what we call band twist. Okay. So, both the cases, in the previous case we had a simple anti-parallel to x axis, and this is uh, outward case, and those two cases, case 1 and case 2, are distinct in terms of that how the bands twist. So, band twisting is nothing but the how the wave functions looks like as a function of k in when you look at in terms of vector fields. Okay. Now, so now the important question is, so let me write thus. Remember, we are still in a insulating state half filling. Okay. Thus, every insulating state, in our case half filling, so every insulating state is some combination of vectors arranged on a ring. So, in some case you will have all anti-parallel to x, and in some case it will all be, I mean it can orient in different direction in this picture, and if you draw it in a full circle it will be outward, or there can be other weird combination also. You play with the parameters, you play with the hopping parameters and so on, you can have something like this all this also. Okay. So, different cases are possible. So, we are considering two extreme limit, right. One is there is only intracell hopping element case 1, and another one is intercell hopping element case 2, and there can be all possibilities within these two cases, right, when both the intracell and intercell are present, and it depends on the relative magnitude between these two hopping parameters. Okay. So, now the question is okay. So, question, deformed from another. So, I have a two vector field, one is this one and second one is this one. So, can I smoothly vary or change the vector field so that I can go from case 1 to case 2 or the vice versa, right. So, is it possible? So, the question essentially becomes, can the vector, I can interchange the or rearrange the vectors of type 1 so that I go to type 2 or case 2. In terms of physics, it is essentially implies that can I go from trivial insulator to topological insulator, or the vice versa, right, because that case 1 is trivial insulator and case 2 will be topological, as we will see in next few minutes. Okay. So, this is the important question that we will answer, and in order to answer this question, another important point that we need to keep in mind, that there we cannot have any gap closing physically. So, we had an insulator type 1, let us say, or case 1, and then we had again another insulator of type 2. Now, can we go from this one to this one or this one, let us say, without any gap closing? Why gap closing is important, it will be clear. So, let us say suppose we have a insulator and you are going from this to this. So, this was type 1 and this is type 2. Type 1, type 2 so far is in terms of the vector field. Okay. So, in case 1 type, okay, so I am mixing between case 1 and type 1, those are same. So, in case 1 we have vector field, simple vector field, and in case 2 vector fields are outward with each other. Okay. So, can I go from case 1 to case 2, another basically same wave function or same band structure without any gap closing, meaning in between there will be no state like this one. Let me draw more carefully. So, this is not allowed. Okay. So, this is the gap closing point. So, this is not allowed, not allowed. Why not allowed? Because then these two states will be degenerate. So, at the gap closing, exactly at the gap closing, the two states, we had a two states always, minus t and plus t. So, two states will be degenerate. Okay. So, when two states are degenerate, so any combination of any linear combination of these two states, so any linear combination of those states can be a valid state. Okay. And because of that, theta and phi are not well defined. Why theta and phi are not well defined? Because when we are doing this I mean vector parameterization or vector orientation, we are only seeing or we are only observing the ground state, right? Here equation C for the case 2 and equation B for the case 1. Now, when the gap closes, that means at that gap closing point, any linear combination of states are a valid states. Now, you cannot particularly assign theta and phi at that point, right? Or another way to look at this, when the gap will close, the gap will close in our case at the epsilon equal to 0, right? Now, when epsilon equal to 0, the vector has no value. So, remember this was the Hamiltonian and Hamiltonian. So, the vector's magnitude, so the magnitude of this vector was unity, right, and in our case it was minus t. So, mod of minus t is simply plus t and so on, and direction was determined by theta and phi. So, when the gap closes, then epsilon equal to 0. Now, epsilon equal to 0 and epsilon determines the magnitude of this vector. So, vector itself is 0. So, basically in other words, it is saying that it is not well defined at that particular situation. So that is why we say, or our I mean point is ki can they be smoothly deformed from one to another. I mean, can I go from case 1 to case 2 without any gap closing, because if the gap closes in some in between states, the whole formulation is not valid, right. I mean, I am arranging the vectors and seeing that okay, for the case 1 and case 2 vectors are arranged in a completely different manner and so on. So I am trying from, let us say, case 1, this case 1 and case 2, and at some point if the gap closing happens, uh, the whole framework just breaks down. Okay. So so basically, in a way we are asking that if one insulator of type 1 or case 1 can be made another insulator, in our case 2, without gap closing, right. So so whenever there is a gap closing, the vectors cannot be smoothly deformed, because in between the states, the moment there is a you hit the gap closing point, the vectors are itself ill defined, because again as I said, the vectors magnitude are determined by the that energy eigenvalue. So energy eigenvalue itself is 0, and then you have linear combination, all linear combination as possible eigenfunction and so on. So that is not allowed. So yeah. Now, in order to characterize such vector, okay, so it turns out that you cannot go from case 1 to case 2. So case 1 to case 2, you cannot go from case 1 to case 2 without any I mean, if you do not have any I mean, you cannot simply go from case 1 to case 2. Now we ask, so so we have already seen the vector profiles and how wave function, right, it is essentially determined by the wave function. Energy eigenvalues are same, remember that energy eigenvalues are same, so things are still half filled, and you have insulator in case 1 as well as case 2. So what is the difference? Difference is in the wave function and in the vector field mapping. And now how do I characterize these two situations, case 1 and case 2, right. I want to know how these, I mean, how a insulator or a insulator is a trivial or a topological, without studying or without worrying about all of these in between details things. This is a very simple case. I mean, I took only intracell hopping to be finite, and then I took intercell hopping is 0 for case 1 and the vice versa for the case 2. But in practical things can happen that both are there, intracell and intercell. There are some difference in magnitude, or there can be same also. So what is the quantity that we can define so that we can characterize these two different types of insulator more easily? So then comes the question of winding number. Okay. So winding number, and it is defined as omega 1 by 2 pi 0 to 2 pi or minus 2 pi minus pi to pi, whatever you want to take. So I am taking theta, so it is better to take actually minus pi to pi, but let's not confuse this from this for the polar coordinate. So n cap of theta, I'll explain what are these n cap of theta and so on. Del theta, n cap of theta, okay. Okay, so yeah, k cap, okay. So this is the winding number, and this tells us the total phase gained out of a twist in the vector field. Okay, so I have a let's say oh sorry, so I have a vector, let's say it can be pointed anywhere. uh, so so these are simply vector fields twisted, basically they are not parallel. So I have so let's say somewhere the vector is look like this. So now I am characterizing the vector's direction of this vector as so let me use different colors. So this is, let's say, phi, and so perpendicular to it and connected with the center, and this is theta. Okay, okay. Okay, so so essentially for this kind of vector field, uh, theta is different. So you have a gradient of theta, I mean gradient of n with respect to theta, right? So del theta of n cap theta. So n cap is just the direction. So this is one n cap, this is another n cap oriented along different direction. So del theta of del n theta is non-zero here, right? Had it been all parallel, so let's say all are parallel, I have a circle and all parallel, this del n del theta n cap will simply be 0, because there is no variation with respect to theta, all are along the same direction, right? So you can already guess that I mean for the type 1 or case 1, we have a winding number equal to 0, because del theta of n will be 0, all because the vectors were oriented all along the same direction. And in case of case 2, intercell hopping, we had some finite winding number. We will calculate what will be the winding number, but then you will have this case, right? Del theta of n theta is non-zero. So there is a chance that you will get some finite number, and that is what characterizes the two insulator case. One is trivial, where winding number is 0, all the vectors are along the same direction, parallel or antiparallel to the x, and in another case there is a twist, there is a band twisting happens, the vectors are oriented in a different direction, and there is a finite winding number. Okay, so this is what, and then whenever there is a finite winding number, we call it topological insulator. Remember again that both were insulator, but there is a finite winding number in the second case. Okay, so if we calculate yeah, so just to calculate the winding number, so here we are talking in terms of theta, but in our case, remember that what was the varying parameter. So we had one wave function for the trivial case or case 1, we had 1 by root 2 1 1, right? And then for the, so this is case 1, this is case 2, we had 1 by root 2 1 e to the power minus I k. So what is the variation parameter? So theta is essentially k in our case. So theta is general. So this is the general formula that what is the total phase gained out of a twist in a vector field. So a general vector field, nothing to do with physics, topology and so on, I mean topological insulator and so on. So you can kind of calculate the phase from the vector field of the vector field from this expression. Now in our case, in our case the wave function, I mean the parameter is simply k, right? So the varying parameter is k. So we had e to the power I phi equal to minus e to the power I k. something like this, right? So for our case, a momentum space winding number formula is simply uh, given by 1 by 2 pi minus pi to pi. Again, these are k parameters, right? Minus pi to pi means, okay, so this will be theta equal to 0 to pi. So I just confused. So 0 to 2 pi, because theta can be 0 to 2 pi, right? So you start from here, let's say 0, and you go full round 2 pi. Now for our case, in the momentum space or condensed matter picture, in the Brylin engine picture, in 1D it just varies from minus pi to pi, right? Or actually it goes from minus pi by a to pi by a, but we consider a equal to 1, unit cell length is 1, dimension is 1, so it is minus pi to pi. So dk, and it will simply be n of k cross del of k, theta is replaced by n of, I mean k, n of k dot z cap, k cap means z cap, let's say, but k is already momentum, so I'll write as z cap, and that's it. You just need to compute the integral. So 1 by 2 pi. Now minus pi to pi. So what is n of k here? In our case, n of k is simply e to the power ik or minus ik, let's say, right? So e to the power minus ik means cos k x cap. Again, remember that we are in the x, I mean xy plane, and plus sin k minus, it will be minus sin k y cap, right? So we have something like cos k minus I sin k. I have written I, no, x cap, and y cap I sin k cross del k of same thing, cos k x cap minus y cap I sin k, and dot z cap, right, and dk. So 1 by 2 pi minus pi to pi dk x cap cos k minus y cap I sin k cross it will be simply x cap cos k is minus sin k, and then it will be minus y cap I cos k, right, dot z cap. So 1 by 2 pi minus pi to pi dk. So x cross y is simply z cap, sorry, so this one and this one, cos square k, and then this will be plus y cross x is again minus z, so I am in trouble by a iota factor, right? Okay, actually I should not replace eta, I mean nk e to the power minus ik as simply the exact value of it, cos k x cap minus I sin k y cap. Okay, so this is just the representation. So actually what I should do is that so let me remove this. So what I should do is simply take this u of minus k, u of minus k. So you need to do so something like this will be there, right? And cross, you take a gradient, actually grad k, but this is in 1D, so no issue. uh, so grad k u minus and dot z cap, let's say, right? And you integrate this minus pi to pi 1 by 2 pi, and then if you calculate it will be 1. You cannot just take it to the power minus ik. Okay. Okay. So so and in the first case also we already know that winding number will be 0 because of del theta of n cap theta is simply 0, or because of the reason, sorry, because of the reason that del k of u minus k in this case, uh, in the in this case it's simply 0, right? There is no k dependence. So we have seen that even though those are I mean there can be two insulator, they can be distinct, and wave function determines this property. Actually from the wave function itself we can calculate something called winding number, and already tell that a that insulator is topological or non-trivial, or the insulator is trivial, that is winding number is 0. Okay. So so basically the root is in the band twisting once we draw these vector fields, but these are very sort of I mean very tough to calculate things, right? I mean you cannot. So for 2 by 2 model it is very easy. You just map to 2 by 2 general Hamiltonian like this one. So this Hamiltonian cos theta, sin theta, and so on, and you map to a 3D polar coordinate system. But once you have higher dimensional Hamiltonian 3 by 3, 4 by 4, and so on and so forth, it is just becomes impossible to visualize things. So so a priori you cannot calculate analytically that is there any vector twist, or sorry, band twisting, the vectors are arranged in along the same parallel direction, or there is a twist in the vector field, and so on. So all of that you don't really need. All of that is for intuitive understanding how there is a band twisting, and the band twisting give rise to a finite winding number. Okay. You just calculate winding number. For that what do you need? You just need the wave function, which you can easily calculate numerically, analytically, and so on. And once you calculate that, you get to know the insulator is topologically trivial or not. Okay. And that's the essence of differentiating, or the whole field of topological insulator is because of this, actually, that although the energy band wise the two insulator can look like exactly same, but they are very different from each other in terms of wave function and winding number, and you cannot go from one to another always. Okay. I am saying always you cannot go, I mean there is no guarantee that you cannot go from case 1 to case 2, because if there is a gap in the system, I mean so how do I say, uh, so we already have gap in the system because we are in insulator, but uh, so it turns out that another case can be considered where you have on site potential at each of those sites. Okay. And if we have on site potential at each of those sites, remember that Hamiltonian that we took uh, didn't have any on site potential. So let me go to the this Hamiltonian. So we didn't have any on site potential, right? We have only A to B hopping and so on. There is no A to A energy or B to B energy, right? So if we have that, it turns out that you can go from one state to another state without any situation of gap closing and so on, but those are more fine minute details. Yeah. So basically just in terms of vector manifolds, the quantities the quantities of this winding number are called topological numbers. Now for 1D case we call it winding number, for 3D or sorry 2D case we call it Chern numbers, and so on. Okay, and depending on the symmetry of the system and other details, these topological numbers or topological invariants can be different for different symmetric system. There is something called Z2 topological insulator, or Z2, basically there the topological number is Z2 instead of Chern number or this winding number. Okay. Okay, so an important point is that these topological insulator are distinct because although their bulk remains insulating, uh, but in the bulk there is a I mean gap between the two bands. Their edge state conducts. Okay, and how many edge state, edge mean at the physical boundary of the system. So although we always consider I mean periodic system and infinite, there is no boundary and so on, but in realistic system you will always have a boundary. So edge states mean the states that lies at the edge of the sample, physical edge of the sample. So in case of topological insulator, those edge states conduct and bulk remains basically non-conducting. Okay, so that makes them non-trivial, and there are zero energy modes, I mean zero energy edge modes, which can conduct electricity without any dissipation and so on. Okay, that's why these kind of things are interesting. Okay, so we'll stop here. I have not done or I mean mentioned anything about the I mean solution for the week 3, I mean quiz solution, but you can email me at sunitd@ac.in. So if you have any difficulty, although I find that almost all the questions are solved or given enough amount of hint in the class itself, the quantum Hall effect classes, there are I think 4 lectures, but even if you cannot solve the problem, you just email me at sunitd@itk.ac.in, and I'll try to reply within a day itself. Sorry. And if you have any question, just let's discuss in the next session. Okay, so I'm ending the meeting.